Okay, hello everybody. What we're going to do today is a bit of a review type thing. So, nobody really sent me anything in particular that they wanted to see in the review guide. So, what I decided to do is I'm going to go through this sort of study guide, which another instructor was kind enough to put together for everybody. And then I'm going to do a practice final exam from another section of another year of this class. And hopefully should cover almost everything that we did in the class. So yeah, let's go ahead and start. So first of all, don't forget your final exam is going to be on December 9th from 9 a.m. to 9 p.m. It's the usual format. I'll give you 12 hours to download the exam. You can print it out if you want, fill it out, whatever. You can fill it out on a sheet of paper, loose leaf, whatever. Just make sure when you're done, you use some kind of scanner or scanning app on your phone or something to go ahead and scan that into a single PDF and submit it to the Blackboard page no later than 9 p.m. that night. Okay, so I think that's all I have to say about that. So let's jump into the material. So this just kind of goes down section by section. We can talk about each of these things here. So section 1.1, that was back when we were dealing with just determining whether a graph is a function or not, determining whether a data set represents a function. And we had some work on things like these, like determining the shape of the graph based on the description of a scenario. So taking a word problem and then drawing the graph of what's going on with some function which is implicit in this word problem. Determining where a function is increasing or decreasing from its graph. Well, does it look like it's going down or does it look like it's going up? Well, in one case we have that we are increasing, and in the other case we have that we're decreasing. So we should be able to look at even a curvy graph and decide whether we think in certain places where is it increasing or decreasing based on whether the height of it is going up or down. Okay, we also want to be able to find function values, vertical intercepts, and horizontal intercepts from a graph. So let me just remind you, if we have some graph, I'll draw it up here, of some function, which I'll do in red, then our vertical intercept can be seen here in purple. It's the point at which the function crosses the vertical axis. Most of the time the vertical axis is the y-axis. And then in green here we have a horizontal intercept. That is where the graph of our function crosses the horizontal axis. Oftentimes x or t will be on the horizontal axis. Okay, so that was intercept and interpreting function values, vertical intercepts, and horizontal intercepts in terms of a word problem. So what we're interested in doing here is taking a word problem and if we have, say, some function, maybe we can use this one as an example. Say this was the function d of t, where d was on this axis and t was on this axis. And if we were told that d of t represents distance from home, then the interpretation of d becoming 0 means we arrive at home. Okay, so taking functions in the context of word problems and interpreting events that can happen to these functions in terms of what those events represent in the real world scenario. Okay, section 1.2, you want to be able to find components of a line. So we need to know slope, vertical intercept, horizontal intercept. That's pretty standard. We should be able to find the equation of a line given 2 points using either y equals mx plus b or point slope, which I'll remind you, point slope is y minus y naught equals m times x minus x naught. So if we have the point and the slope, then we can write down the equation of this line. Okay, we should also know how to graph a line if we have the equation. And we should be able to find the equation from word problems, and we should be able to interpret all of these various properties of a linear function in terms of the word problem. Okay, so section 1.3, don't forget we need to know how to find the average rate of change. The average rate of change on A to B. We have average rate of change is equal to f of b minus f of a over b minus a. So that is how we find the average rate of change. It's also known as the slope of the direct path, if you remember that. And we should be able to do word problems using this method. And let's see, we should also, well, yes, this part is sort of important. We should be able to determine whether a function is concave up or concave down from its graph. Okay, so remember, the way we do that is just by looking at the word up. In the word up, the u here is what it looks like to be concave up. We're sort of bending upwards. And then in the word concave down, we take a look at this n here, and in the word down, this n is in the shape of a concave down graph, okay, bending downwards. Okay, so section 1.4 was all about cost and revenue and profit functions. Specifically, section 1.4 was really just about linear cost, revenue, and profit functions. We later expanded our understanding about those functions to be more interesting, wiggly looking things, but for section 1.4 we were really just interested in linear ones. And we needed to know how to find the marginal revenue, cost, profit, etc. It was just equal to the slope of the profit, revenue, cost functions. So the marginal cost, marginal revenue, and marginal profit was really just a number as long as the cost, revenue, and profit functions are lines, because the slope of a line is unchanging. Okay, so finding the break-even point. So break-even point is going to be when your costs are equal to your revenue. Well, if we have profit equals revenue minus cost, and we have revenue equal to cost, then this will be equal to 0. If we have this equal to 0, our profit equal to 0, that's our break-even point. So we want to find the value of Q that's going to make that happen. Okay, and then finding budget constraint equation from word problems. I would just say, I would reword this as understand marginal, in parentheses, marginal cost, revenue, profit functions in word problems. Okay, section 1.5, we started to learn about exponential growth and exponential decay. So we should be aware of the formulas P equals to P a to the t, P naught a to the t, and P equals P naught e to the kt, where this top one we called annual, growth, or monthly or daily or whatever. And the one with the E is the one that we called continuous. Okay, so we should know how to find the equation of an exponential function from a word problem, and just how to manipulate these equations and solve them for unknown constants. We'll see an example of that later. Okay, in section 1.6, right after we learned about the exponential function, we learned about the natural logarithm, and a really important fact about the natural log is that it isn't the inverse of, let me add a page. The important thing we learned about ln is ln of x and e to the x are inverses. And what that means is that if we take the natural log of the function e to the x, it undoes what e to the x did. So we gave e to the x x, and e to the x spat out e to the x, and now we're going to undo that action, so what we're going to get back is just x. And same thing in the other direction, e to the ln of x was just equal to x. Okay, so for example, natural log of e to the 32 is equal to 32, and so is e to the ln of 32. Okay, so we should know how to apply the natural logarithm to numbers. We should know that the results of applying the natural logarithm to a number will give us a number. If we take ln of 6, that's going to be a number. We can do it in our calculator and we'll get some decimal. Let's see, we should also know how to apply the properties of the natural logarithm, specifically the sum rule and the difference rule. So if we have ln of a sorry, one sec. If we have ln of a plus ln of b, then this is going to be equal to ln of a times b. And that was rule number 1, I think. Rule number 2 was probably the difference rule, where if we have ln of a minus ln of b equals ln of a divided by b. And then finally, we had the power rule, which was that ln of a to the power p should be equal to p times ln of a. And this is really the most important one. In fact, you can deduce the other two from this one. But really, this is the reason that natural logs were really even invented, was to sort of get these powers out front. When we have an equation where we want to solve for a power, we really need natural logs. Okay. So, yeah, we should know how to do word problems with logs. We should know the difference between growth and decay rates and continuous growth and decay rates. So in particular, we have these two situations where we have p equals p naught e to the kt, where in this case the rate is k times 100%. And in the other case, we had p equal to p naught e to the kt, sorry, not e to the kt, but just a to the t. And we said that a is equal to 1 plus r, and the quote rate was just r times 100%. And the key thing to know is that if we compound continuously at 7%, it's not the same as compounding annually at 7%. They'll be similar in most cases, but not identical. Okay, so we're down here now on this one. So lastly, we had converting between exponentials, functions with a rate, this should say annual rate, and a continuous rate. So yeah, then 1.7, we need to be able to use exponentials and logs with word problems. Okay, section 1.8, we learned about composing functions, so we should know how to do f of g of x and so on and so forth, and we should know how to express a function as a composition of functions. We should know how changes to a function affect its graph, so we should know how, for example, vertical stretches work, horizontal stretches, horizontal shrinks, vertical shifts, horizontal shifts. We should know all of these graph transformations on how those are going to affect the graph of f of x. So that's 1.8. 1.9, we learned proportionality and inverse proportionality. And we should know how to understand how quantities are going to be changing when we are given a word problem which says that some quantity is inversely proportional or directly proportional to some other quantity in the word problem. And we should know how to find the equation of a power function. Given 2 points, you guys should be able to figure it out, but really just I want you to know what is a power function, what does it look like, and also a polynomial. So if you don't remember the definitions of power functions and polynomials, that's definitely something to review. Okay, chapter 2 was when we started to learn about derivatives. And we initially started to learn about derivatives in terms of what we called, quote, instantaneous rate of change. And we had this really bad way of approximating it, where what we did was, I'll try to draw a little picture here. What we did was, if we wanted to know the instantaneous rate of change at this green point, what we did was we took successively closer secant lines, so lines like this, and we found the average rate of change between these 2 points. And then we just moved this purple point up and got closer and closer and closer and just kept finding these average rates of change between these 2 points until the points were so close together that they were, virtually indistinguishable. Let me use blue maybe. And then we got to a point where it was looking kind of like the tangent line. And that was how we computed instantaneous rate of change. So I do want you guys to know how to compute the derivative using this method. If I'm not going to ask you a question where I'll say, I want you to compute it in this particular way over another way, but I may give you a problem where there's really no other way to do it. So there's ways that if I give you certain information, you'll be able to use this method, but you wouldn't be able to use, say, your typical derivative rules to compute this instantaneous rate of change. Okay, so that's that. We should know what the derivative means graphically. It's going to represent the slope of the tangent line. The difference between average rates of change and instantaneous rate of change, kind of implicit in what I was just talking about. Section 2.2, we learned what the derivative means graphically. Just talked about that. Knowing what the sign of the derivative tells us about the graph of a function, so that's important. In particular, if f prime is larger than 0, this tells us f is increasing. And if f prime is less than 0, this tells us that f is decreasing. Okay. Identifying the graph of the derivative function given the graph of the function and vice versa. So we should be able to look at the graph of a function and sketch, basically, the graph of the derivative of that function. Okay. So finding a better approximation for the derivative. I'm going to cross that out because I don't know what that's talking about. That might be something specific to their class. Okay. So, my MacBook just went to sleep. Hopefully we're good. All right, so 2.3, we should know the different notations for the derivative. Okay, so remember we called them Leibniz versus Newton. For Leibniz notation, we had things like dy dx or dz dt, stuff like that. And for Newton, we had things like f prime of x or g prime of t. Those sorts of things. And approximating function values from the function value and the derivative value at another point. Okay, so this is talking about tangent line approximation. Okay, so we should know how to take the function value at a given point and its slope to find the equation of the tangent line. And we should recognize that when we're very close to this red point here, say if we're at this green point, the value of the tangent line will be close to the value of the function itself, as long as the green point, in terms of its x value, is relatively close to the x value of the tangent line approximation. The further out we go, the worse we're going to get. I'm going to do an orange point to demonstrate that. The further out we go, the worse the tangent line approximation gets. So, just to remind you, the formula for the tangent line is t of x should be equal to f of a plus f prime of a times x minus a, where a will be some value which is known. It's going to be the x value at which we are performing our tangent line approximation. And you'll be able to compute f of a and f prime of a. Typically, they'll either be given to you or you'll have the function and you can compute them yourself. Okay, where was I? I think interpreting function and derivative values in a word problem. We should definitely be able to do that. Knowing what a graph looks like that is concave up or concave down, I already talked about that. And knowing what the sign of the second derivative tells us about the graph of the function, well, we decided that f double prime larger than 0 tells us that f, the function f, is concave up, and f double prime less than 0 tells us that f is concave down. So that was the second derivative. Okay, and then 2.5, approximating cost and revenue values from the cost and revenue values and marginal cost and revenue values at another point. Okay, so this was really where we started to sort of incorporate cost, revenue, and profit functions which are not strictly linear. Okay, so this was average rates of change and instantaneous rates of change of cost, revenue, and profit functions. Chapter 3, let's see, 3.1, 2, 3, and 4, I believe, were just derivative rules, basically. So sum rule, multiplication rule, or multiplication by constant, product rule, quotient rule, chain rule, all of these different rules. You definitely need to know all of those and how to compute derivatives using those rules. Okay, then chapter 4 was all about local extrema, okay? So finding critical points. We need to know what the definition of a critical point is. We should know that a critical point is not necessarily going to correspond to a max or a min. However, a max or a min will always be a critical point. Okay, we should know how to find inflection points. Remember, inflection points, f double prime greater than, or f double prime equals 0, prime double prime of x equals 0. This tells us that x is a candidate for an inflection point. Remember, the actual definition of an inflection point is where f double prime goes from being negative to being positive, or goes from being positive to being negative. Okay, we should be able to determine concavity from an inflection points of a function given the graph or given the equation. Okay, so we can use things like a number line. Okay, so we can make a number line, and if we decide, okay, to the left we have f double prime greater than 0, and then to the right we have f double prime less than 0, then we know we're going to have an inflection point at that point. Okay, then we should be able to find global maximums and global minimums on closed intervals. So I'll get rid of this open thing because I didn't really talk much about that. So we'll do just global minimums and maximums on closed intervals. And we should be able to solve word problems with minimization and maximization. We should be able to incorporate our understanding of minimaxing functions to minimaxing profit, cost, and revenue functions as well. I guess one thing that I would really want to put in here is make sure you know the first and second derivative tests for critical points. First and second derivative tests for critical points tell you whether a critical point is a max, a min, or neither. Okay. Section 4.4 we just talked about. Okay, so now we're on to chapter 5. Okay, so chapter 5 and 6 were really all about integration. And the way we sort of started the integration chapter was by learning how to do Riemann sums. Okay, so we should know how to do Riemann sums, both left and right, and left and right Riemann sums. We should know how to do Riemann sums based on a word problem that tells us how many rectangles to use. We should also know that delta x is equal to b minus a over n. And we should know that this represents bits of each rectangle. And we should know that n is the number of rectangles. Okay, so let's see here. Expressing total change with notation. We should know what the definite integral means. Specifically, we should know that it is the limit of the Riemann sums when we use more and more rectangles. The mathematical way we write that down is we say n is going to infinity. The number of rectangles is going to infinity. Okay, so that's what the definite integral means. I guess maybe what I will do now is go down to 6.2 because that's the order that we did things in. So after that, 6.2, we learned how to use the properties and rules of antiderivatives to integrate. Why don't we say to find the indefinite integral of f of x, some function. And then in 6.3, we learned how to use antiderivatives and the fundamental theorem of calculus not such good kerning on that. And the fundamental theorem of calculus to do what? To compute definite integrals. And we should know the difference between an indefinite integral and a definite integral. Then we went back, I think, to 5.3. 5.3 was just really more fundamental theorem of calculus. That's what it was. And also finding the area between two functions. And really also knowing the difference between, man, I thought there was somewhere on here where it had that difference between, here it is, yeah. Finding the total area between a function and the x-axis versus the definite integral, okay? So that's something that I want to touch on really quickly. Remember that if we have a function which goes from a to b, then the integral from a to b, f of x dx, is going to be equal to the area which is above the x-axis, and we will subtract from that the area which is beneath the x-axis. So we'll take the green part, and we will subtract from it the red part. So if we want to find the area that's trapped between this function and the x-axis, the total area, then what we'll need to do is call this point C. Spam risk. Okay, we'll need to take that point C, and we'll say that the area, total area, trapped is going to be equal to, well, what we really want is the green area plus the red area. Well, we can express the green area as just the integral from a to c of f of x dx. And we will add to that, what we want to write now is some positive number which represents the area of the red shaded part is going to be not quite the integral from c to b of f of x dx, because that would be a negative number, so I'm just going to put negative of that thing. If I take the negative of a negative number, it'll become positive. Okay, so let's see, where was I? 5.4 and 5.5, we should know how to compute more definite integrals and apply definite integrals to word problems. We should understand that integrating a rate of change will give us some value expressing the total change over a time period, and we should know how to find the units of our word problem, or of the result of an integration. We should know how to express that in terms of the units of the word problem. Finally, I think we learned 6.6, and we should know how to use U substitution. We should know how and when to use U substitution. Okay, so I think that is pretty much a good summary of the things that you're going to need to know for this exam. We'll say, as always, disclaimer, this is not a completely 100% comprehensive video that's going to tell you if you just know all of these things, you're guaranteed to know everything that's going to be on the exam. Some of these concepts will be cleverly disguised in word problems, or in problems with tables, or in problems where you have to grade the work of a fictional student and these sorts of things. So, you know, a regular old familiarity with these concepts is not enough to guarantee an excellent grade on the final exam. What you really need to do is master these concepts through practice. Okay, so the number one thing that I recommend that you do is practice problems. You can practice them on the Wiley Plus page on the Read, Study, and Practice section. They'll tell you whether or not you got your answers wrong or right, and you can check yourself. And what I would really recommend the perfect student to do would be do practice problems on Wiley Plus and make a note of all of the ones that you get wrong and can't figure out why you got them wrong, and bring that list to office hours on Friday and come and ask some questions on Friday. So that's my recommendation to you guys. I'm going to stop this video now, and I will start another video which will be me solving the practice exam.